Hello and welcome back to the video lecture series on the chemistry of heterocycles. Last time we were talking about the chemistry of five-membered rings, and continuing with that, this time we are seeing a reaction where a pyrrole ring is reacting with acetone under acidic condition. This reaction is a curious one because it leads to a formation of a cyclic tetramer where 4 pyrrole rings and 4 acetone molecules are assembled to form a macrocycle. The reaction starts with basically an electrophilic aromatic substitution. Acetone is the electrophile. It gets protonated in presence of this hydrochloric acid and acts as the electrophile to react at the alpha position of one of the pyrrole molecules. After proton release, we get an alcohol. There is an alcohol in the side chain of the pyrrole, which itself can lead to a resonance stabilized tertiary carbocation. If we protonate this OH, this water molecule will leave, and that will be assisted by the nitrogen lone pair. So we get another potential electrophile. This electrophile will react with another molecule of pyrrole. Typically, again, the alpha position will react because we have already established that the alpha position is more susceptible to electrophilic attack for this pi XS 5-membered rings compared to beta. Therefore, another round of aromatic electrophilic substitution proceeds to give you this compound where one acetone molecule has combined 2 pyrroles. This goes on with introduction of yet another acetone on the alpha position of any one of these rings, which again loses a water molecule to give the electrophilic species, which reacts with yet another pyrrole molecule, so on, till a cyclic tetramer is produced. Now a question may be asked that a polymer, this could result in a polymer where a number of pyrrole nucleus and a number of acetone molecules would have been incorporated in a linear fashion, so that we would have got a polymer, but that does not happen. Why is that? In this regard, I would ask you to recall the Thorpe-Ingold effect, that means the gem dialkyl effect. Because of the presence of these gem dimethyl groups, geminal dimethyl groups, the cyclic tetramer formation is enthalpically as well as entropically more favorable compared to the reaction taking the course of a polymerization. Because of these gem dimethyl groups, you have a situation where the cyclization, that is the cyclic tetramer formation, is more favorable thermodynamically compared to linear polymer formation. That is why we get the tetramers. As we know that presence of these dimethyl groups will force the molecule to close down the ring, because the number of possible conformations that the acyclic precursor may have is severely restricted, and it is forced into a conformation where cyclization is the better option compared to polymerization. That is why we get this cyclic tetramer. The next reaction is yet another aromatic electrophilic substitution. This time it is a ipso substitution. If we take pyrrole or furan 2 carboxylic acid, then heating it gives rise to easy decarboxylation, which is in this case a proton is the electrophile. As we know that furan 2 carboxylic acid and pyrrole 2 carboxylic acid are themselves sources of protons. So therefore, this is a very easy reaction for these molecules. If you heat these molecules, Then it undergoes the proto-decarboxylation, where proto means proton is the electrophile and the leaving group is carbon dioxide molecule. So this undergoes proto-decarboxylation and aromatic electrophilic substitution, precisely an ipso substitution, to give you the corresponding 5-membered heterocyclic ring where a hydrogen has replaced this CO2H group, and you get from pyrrole to carboxylic acid you get pyrrole, from furan to carboxylic acid you get furan. Similarly, if furan to carboxylic acid is treated with alkaline iodine, then also we get a iodo decarboxylation. That means the CO2H group is replaced by iodine. Naturally, in presence of this hydroxide, the very first reaction that will happen is the abstraction of this acidic proton, and you get the corresponding conjugate base. This we know is extremely susceptible to the alpha attack, and it undergoes the alpha attack at the position where the carboxylate is present. After the alpha attack, the carboxylate will leave, regaining the aromaticity. We get the iodo 2-iodo furan, and the reaction is driven by the favorable entropy where the carbon dioxide gas is produced inside the medium and escapes. These being the electron-rich pi-XS heterocycles, most furan and pyrrole derivatives are unreactive towards nucleophilic reagents. They are very reactive towards electrophiles, but they don't like to react with nucleophilic reagents for obvious reasons. However, there are exceptions. There are some derivatives that have strongly electron withdrawing group present in them, which are found to be susceptible to nucleophilic attack. And therefore, we have quite a few examples of aromatic nucleophilic substitution on substituted furan and pyrrole. Here we describe 3 of them. In all cases, at a proper position, there is present an electron withdrawing group. And with respect to that electron withdrawing group, at their para positions, because this is ortho, with respect to this magenta colored electron withdrawing group, this is meta and this is obviously para. There is present a potential leaving group. We are using more or less strong nucleophiles in this reaction medium, and we are getting via the corresponding negatively charged intermediate, the so-called Meisenheimer complex. So such is the name of the intermediate that is involved for the aromatic nucleophilic substitution of benzene rings, benzene derivatives. We get these compounds, we get these substituted products. Now, those heteroaromatics that actually undergo nucleophilic substitution, they are found to be more reactive compared to benzene derivatives, and this is rationalized in terms of the lower amount of resonance energy that is associated with these 5-membered rings compared to benzene. So when they react with nucleophiles, the corresponding negatively charged intermediates are formed easily, relatively easily, because the loss of resonance energy is comparatively lower. But an interesting reaction happens with these heteroaromatic compounds, and that mechanism is something that you have not seen before. It is the ANRORC mechanism, which is the acronym or abbreviation of the sequence of events that happens. These reactions are collection of 3 events. The very first event is addition of nucleophile. So we take A and N from this. Then there is ring opening. So we take R and O from this. And the end game is ring closing. We take R and C from this. So this is the ANRORC mechanism. So for a activated heterocycle, that means some heterocycle ring that has a electron withdrawing group on itself, that undergoes a nucleophilic addition. Then a ring is opened, the ring structure is opened, followed by the closure of the ring at some different position so that a different structure results. A typical example is the reaction of 2-acetyl furan in methanolic ammonia when the reaction is done in sealed tube under high pressure and high temperature. The product of this reaction is 2-methyl 3-hydroxyfuran. Therefore, a considerable change has happened. The 5-membered ring has been expanded into a 6-membered ring, and from a oxoheterocycle we now have as a heterocycle. From furan we have pyridine. How does it happen? Well, the very first thing is the addition of nucleophile. The nucleophile adds onto the alpha position of the 2-acetyl furan, the alpha position where the unsubstituted alpha position, and their negative charge is delocalized over this carbon. Now this pushes and this carbon oxygen bond is opened up. That means this is the ring opening stage. To be precise, this is actually a vinylogous substitution at this carbonyl carbon, sort of vinylogous substitution via addition elimination. If you look at the structure of this derivative, furan 2-acetyl furan, carefully, this is a vinylogous ester because this carbon has a carbon oxygen bond conjugated with this, and just like an ester molecules undergoes amidation reaction when it is heated with ammonia via the addition elimination pathway, the nitrogen lone pair attacks here, the C double bond breaks, we get a tetrahedral intermediate with a negatively charged oxygen that eventually pushes back and this alkoxide leaves. We get the amide. That's the addition elimination pathway. This is the same pathway except for the fact that it is a vinylogous variant. The result is a ring open product which can be called a vinylogous amide because this nitrogen is conjugated with this carbonyl via these two double bonds. Also, we have an enolate here. So let's protonate this enolate because there is proton source in the reaction medium. It will undergo protonation and it will undergo it will become the corresponding carbonyl. Now look carefully. You have NH2 group, a COMe, and alpha to that COMe is another carbonyl which increases the electrophilicity of this carbon. This time the ring closing will take place. This nitrogen will attack this carbonyl and we will get a tetrahedral intermediate from where we can eliminate the water molecule between these two atoms and shift one hydrogen from this alpha position onto the carbonyl oxygen and correspondingly reorganize the pi electrons to get the corresponding enol derivative, and that is favorable because the ring will now become aromatic. This is a very important problem and it has appeared in the university question papers on many occasions. So I suggest that you practice this mechanism and assimilate what is happening in terms of the nucleophilic addition elimination of vinylogous ester, and then followed by ring closing, followed by aromatization. Similarly, I have given you another example. Basically, the reaction is basically the same. Again, ammonia will attack here. This time again, it is a vinylogous ester. Ring opening will take place, and then followed by ring closing, you will get the corresponding pyridine derivative. When we were talking about aromatic electrophilic substitution of these 5-membered rings, we discussed the point that their reactions with conventional reagents that are used for the SEAR reactions of benzene derivatives, they are mostly incompatible. The reagents needs to be modified. You cannot nitrate furan or pyrrole by a nitrating mixture. Well, that is because competing side reactions take over and the aromatic electrophilic substitution product is probably a minor product or it doesn't form at all. Because of the pi excess nature of these heterocycles, they are highly susceptible to protic acids and they undergo polymerization under acidic condition. If you control the reaction, even if you manage to control the polymerization, they undergo trimerization. Here we demonstrate for furan you have this type of trimer formation when you expose it to protic acids, even under controlled condition. So here you have a trimer where one furan molecule has in the center has attached two other furan molecules from both alpha positions through the corresponding alpha position of the terminal furan molecules, and the other trimer is the central furan molecule has used one of the alpha position and one of the beta positions to attach the two terminal furans, both of which you have used their alpha positions to form the CC bond. This is the corresponding mechanistic interpretation where you start with protonation at the C2, which undergoes normal electrophilic addition from this blue colored furan molecule at its corresponding alpha position. So you get the C2 C3 bond established. Now this is obviously a vinyl ether, so it will undergo protonation to give you the resonance stabilized oxocarbenium ion. The magenta colored furan will now attack this position to give you the trimer, which is described here. On the other hand, if you take furan and allow it for the protonation at the C3, which leads to the 3H cation, that is definitely less stable, but it is more reactive. The magenta colored furan is now attacking this electrophile through its alpha position. Corresponding aromatization will again lead to formation of a vinyl ether derivative that will be protonated under this reaction medium. The generated electrophile will be captured by the blue furan to give you the trimer that was described here. Similarly, if you expose pyrrole in say 6 normal HCl, and you can see that it is an extremely controlled condition at low temperatures as low as 0 degrees centigrade and only for 30 seconds, you still get the corresponding trimer where the central pyrrole ring has incorporated on both of its sides through both of its alpha carbons. It has incorporated two additional pyrrole units. So the central pyrrole unit is now attached with two additional pyrrole units. So this is definitely a problem, and therefore you must rigorously avoid protic acids under any condition to achieve any meaningful reaction of furan and pyrrole. The other aspect of the reactivity of these heterocycles, as we have told you, because of the lower resonance energy associated with this nucleus, the other aspect is obviously they behave differently from the benzene derivatives. The benzene derivatives, they generally do not behave like a diene or an alkene. They do not behave, although the benzene ring possesses multiple double bonds. The resonance energy of the benzene nucleus is such that such reactions are prevented, because permanent loss of resonance energy is something which the benzene nucleus does not usually suffer. On the other hand, because of the lower resonance energy of furan, its aromatic nature is compromised, and one aspect of its reactivity is something where the ring double bond behaves as if it is part of an enol ether. Like enol ethers, furans are readily hydrolyzed by dilute acid to give you carbonyl compounds, and with furan you get actually a 1,4 dicarbonyl. This is yet another reaction which has been featured prominently in the university question papers. So they ask you to answer this question, that give an example where furan is behaving as an enol ether. So how do you proceed? Obviously, you take a furan derivative and you protonate it at the corresponding C3 position. Although this is the relatively less stable 3H cation, and this protonation is relatively less favorable because C2 protonation would have been thermodynamically more favorable. The C3 protonation gives rise to a 3H cation which is less stable and more reactive. So you remember that when answering this question, you have to first protonate at C3. The normal tendency would be to protonate at C2 because that is the thermodynamically more stable cation, more stable conjugate acid, but that will not give you the desired product. The reaction in this case will happen on the less stable but more reactive 3H cation. Water will dutifully attack here, so you get a hemiacetal linkage established. And if you look at this is a hemiacetal, as well as from this side, from the left side of the molecule, it is an enol ether. So again, you can collapse the hemiacetal by generating the carbon oxygen double bond here, and by protonating the vinyl ether at the alpha position, you can get yet another carbonyl bond, carbonyl group established here. So this is a 1,4 dicarbonyl that is generated from the furan. The furan ring is therefore can be presented as a masked form of 1,4 dicarbonyl system, which reveals the hidden 1,4 dicarbonyl when exposed to dilute acid. That means acid catalyzed hydrolysis of furan will reveal the 1,4 dicarbonyl. How important is this reaction? Very important, because this gives access to 1,4 dicarbonyl compounds, which from your previous experience you know they are dissonant targets, and therefore their synthesis generally requires Ampolon strategy. Here are few examples. 2,5-dimethyl furan. It is undergoing acid catalyzed hydrolysis to give you 2, 4, 2, 3, 4, 5, 2, 5 hexane dimer. With 2-methyl furan in presence of 1.5% hydrochloric acid in methanol, it is undergoing again the acid catalyzed ring opening where the furan is behaving as an enol ether. You get a carbonyl here, that's a ketocarbonyl. You get a CHO here because you only have a hydrogen at this position, and that aldehyde is preferentially acetalized in presence of this alcohol reaction medium, so that you get this compound as your product. As we know that aldehydes are far more reactive, both electronically and sterically, compared to ketones. This is the reaction that we get where the acetal formation has taken place preferentially at the aldehyde. Another important reaction is that of furfural, that is the 2-formyl furan. When furfural is reduced with sodium borohydride, this being an aldehyde group as well as a vinylogous ester. Generally esters are not reduced by sodium borohydride, but this being the half aldehyde, it will undergo smooth reduction to give you furfuryl alcohol. Now, furfuryl alcohol, as you can probably tell, it is very susceptible to acid because this OH can be protonated and it can leave, giving rise to a so-called primary cation. But that's not exactly primary because this oxygen lone pair will support it. This oxygen lone pair will assist in the departure of this OH to give you a resonance stabilized oxocarpenium ion. So when this thing is treated with dilute acid, exactly that is what is happening, and we get where the oxygen is supporting the departure of this OH2 plus. But in presence of water, additional reactions can take place. Water molecule can attack at this alpha position and assist in the departure of this OH2 plus, or you can think in terms of this oxygen has assisted the departure of this OH2 plus, and we have a carbon oxygen double bond here with a plus charge here, and water molecule has attacked at this position, so that the same intermediate will be resulting. If the water is directly attacking before the departure of this OH2 plus, or even if you have made this OH2 plus go away and you have a carbon oxygen double bond here, carbon double bond here, and the carbon double bond here, that electrophile is getting quenched by this water molecule to give you the same intermediate. Now if you look at this intermediate, then this can potentially undergo a tautomeric change to generate another furan derivative, where from the furfuryl alcohol you have now 2-methyl 5-hydroxy furan. This 2-methyl 5-hydroxy furan, one of the tautomeric form is this one, because you are shifting this hydrogen from here to here, and that is a lactone. And also a vinyl ether. From left side this is a lactone, from right side this is a vinyl ether. So at this, in presence of this H3O plus, this will undergo hydrolysis of both these moieties to reveal the carboxylic acid on the left side and the ketomethyl group from the right side. This is a familiar molecule to you. We have discussed the synthesis of this retrosynthesis and synthesis of this molecule via multiple routes in our previous studies. This is known as the levulinic acid. That means 1, 2, 3, 4, 5. This is 4-oxo-pentanoic acid or levulinic acid. Very useful synthetic intermediate used in many synthetic schemes. So I leave it to you to find out how this vinyl ether and lactone hydrolysis can take place. Think in terms of the possible mechanism that is happening in acid catalyzed acidic medium to reveal the levulinic acid. Pyrrole rings, although they are susceptible to trimerization, they are generally not opened up just as easily as the furan rings do. But if you boil a pyrrole sample with hydroxylamine hydrochloride in presence of sodium carbonate in alcohol medium, it may lead to ring cleavage to give you a dioxin derivative. This sodium carbonate is acting as the proton abstractor to free the NH2OH in the reaction medium. And because this HCl is present in the reaction medium, it is also acts as a proton source. So this pyrrole nucleus is undergoing protonation. Again, look carefully, it is behaving as an enamine and it is protonating at the beta position. Although thermodynamically alpha position is protonation at alpha position is more favorable. But this is the 3H cation, which is less stable and more reactive. Hydroxylamine nitrogen lone pair will now attack due to alpha effect. This molecule is extremely nucleophilic, so it will attack here, and you will get a system where you have two heteroatoms attached to the same carbon. So that's a 1,1 dihex system. This will now undergo enamine type reaction with consequent cleavage of the CN bond, where the developing positive charge can be stabilized by this nitrogen. so that imine linkage is revealed here, and you have already established one of the hydroxylamine linkage, one of the oxime linkage. Now this will further undergo reaction with NH2OH to give you the oxime on this side, just as hydroxylamine reacts with carbonyl compounds to give you oxime and water. This time it is reacting with imine linkage, so it will give you oxime and ammonia. In each case, I have highlighted this again. The nucleophilic attack responsible for the ring cleavage that takes place at the alpha position of the more reactive and less stable 3H cation. Further examples of acid catalyzed ring opening. This is known as the Mark-Wald reaction. This time again our starting material is furan 2 carbaldehyde. Because it is an aromatic aldehyde, it can undergo reactions that are characteristics of such reaction, such reactants. Say for example a Nouveau-Nagel condensation. If you treat this with this dicarboxylic acid in presence of a pyridine-pyridine reaction mixture, this is obviously malonic acid, you get alpha beta unsaturated carboxylic acid. When this molecule is treated with methanol in presence of HCl, again ring opening takes place, and you have esterification at this carboxylic acid, ring opening revealing the corresponding dicarbonyl derivative, ester here, carbonyl here, and this double bond has disappeared. So a lot of changes has happened. So how is this happening? How is this happening? This is not exactly unexpected, because the attacking nucleophile is methanol here. If water has attacked, we would have got a carboxylic acid. This time methanol is attacking, therefore we have ester. But what about this double bond? Where did it go? Methanol HCl is not exactly bad for esterification, so we can understand the esterification as well, but where is the double bond? So the reaction mechanism is decidedly complex. Very first thing that happens is protonation at this carbonyl oxygen of the carboxylic acid, and that is assisted by this oxygen lone pair, which in turn gives rise to oxocarbenium ion, which is immediately quenched by the methanol. So we have acetyl linkage here, and we also have a carboxylic acid enol here. So that immediately re-establishes the carbon-oxygen double bond, because that is thermodynamically more stable. So now you have acetyl linkage, as well as we have the carboxylic acid firmly established here, and we have a conjugated carbon-carbon double bond system here. So now aromatization takes place. So now you have a situation where you have included a methoxy group at the one of the alpha position, and you have managed to get rid of the double bond here. This time it will undergo the reaction characteristic of the vinyl ether. So protonation at C3, corresponding oxocarbenium ion quenched by water to give you the hemiacetal, which is hemiacetal cum vinyl ether. At the expense of this carbon-oxygen bond, you can establish this C double bonded O here and a C double bonded O here. So you have your carboxylic acid, where your ester group is established here, carbonyl group is established here, and at the end of the chain you have carboxylic acid undergoing the esterification under acidic condition in presence of the methanol solvent to give you this corresponding ester derivative. However, this is not the only way this mechanism can be drawn. You can very easily start from this point, and try protonate not this carbon but this carbon. If this carbon is protonated, then also we get a resonance stabilized oxocarbenium ion, which is quenched by water, gives rise to a corresponding hemiacetal as well as vinyl ether. Collapsing that will lead to the same carboxylic acid, which will undergo esterification reaction to the final product. So this is a decidedly complicated mechanism. I urge you to practice it multiple times at home or at your leisure time. Now these ring opening reactions have been found to be useful in many occasions. Say for example, we take 2-methyl furan. If you treat it with butyl lithium in presence of dry ether, then this acidic hydrogen will be abstracted. This hydrogen is acidic because the negative charge here will experience the greatest inductive electron pull by this oxygen. However, there is one factor to be considered, which we will consider for not these molecules but for pyridine nucleus, that there will be a strong lone pair repulsions as well. However, it is also true that the butyl lithium will preferentially abstract this hydrogen, possibly because oxygen can form some sort of a coordinate interaction. It can coordinate with the lithium cation to direct the butyl lithium molecule to abstract the alpha hydrogen preferentially. So now you have a carbon ion established here, and we are doing this reaction with the organobromide, which is an electrophile, just an SN2 reaction, and then we are opening the ring. After you open the ring, the 1,4 dicarbonyl is revealed, which is redrawn in this way. Treated with alkali, it will undergo intramolecular aldol condensation to give you the cyclopentanone derivative. The intramolecular aldol condensation could lead to different products. Here we are condensing, forming enolate from here and closing down the ring here, so that we get the 5-membered ring. It is the tetrasubstituted double bond, which is the thermodynamically more stable than the other possible products, that drives the reaction. If you could form the enolate here and close down the ring, it is 3-membered ring. The reaction can take place, but the 3-membered ring being very unstable, the aldol reaction will be reversible and it will immediately open up. The same thing here, if you can form the enolate here and close down the ring here. If you can form the enolate here and close down the ring here, so that's also 1, 2, 3, 4, 5, but that would have led to formation of a relatively less substituted product, less substituted double bond in the product, and that is why that reaction is also unfavorable under thermodynamic condition, thermodynamic control, so that we get the corresponding aldol addition product, which undergoes the E1CV elimination to give you the tetrasubstituted alkene. Because of the lower resonance energy for furan, which is the lowest among the three, that is pyrrole, thiophene and furan series, and presence of the highly electronegative oxygen, we expect the molecule to show some sort of diene-like behavior, which is usually observed in practice. Remember, when we did the nitration of furan, there was one step involved, which was treatment with pyridine. Well, that is because furan, first of all, cannot be nitrated by normal nitrating mixture. That would have led to polymerization, etc., etc. It is done with modified reagents such as acetyl nitrate. When you treat furan with acetyl nitrate, you don't get 2-nitrofuran, but you get something which is a 1,4 addition product. In acetyl nitrate, the possible electrophile is NO2+, and this furan ring will preferentially add this nitronium at this alpha position because of its tremendous alpha directing ability. Instead of acetic acid acting as a base and abstracting this proton, which is expected normally for a sigma complex resulting from a benzene or a benzene derivative, it acts as a nucleophile and adds at the other alpha position. So if this position is 1, which it is not, but let's say if this position is 1, then this position is 4. So that's basically electrophilic agent adds at C1, and the nucleophilic agent, instead of acting as a base, it attacks the C4, so that you get a 1,4 addition product. Only when you treat this with pyridine, a 1,4 elimination will take place, giving rise to aromaticity and the 2-nitro derivative. Let us again consider this, take this example a bit further. This is 5-methyl furan 2-carboxylic acid. Do the same thing. You get two products. One is nitration at this position, which is okay because it is beta with respect to the ring oxygen, not very favorable, but meta with respect to the electron withdrawing CO2H and ortho with respect to the electron donating methyl. So you get 5-methyl 4-nitrofuran 2-carboxylic acid, but that yield is relatively poor. The major product is ipso substitution, where we have nitro decarboxylation. That means nitronium has included itself at this position and a carbon dioxide has been lost. But these two will undergo this reaction will involve formation of the 1,4 addition product, and only with pyridine, workup with pyridine, will reveal the 2-methyl 5-nitrofuran. So the nitro group has been incorporated here. This is alpha with respect to oxygen, ortho with para with respect to methyl, and we get this 1,4 addition product. And this carboxylic acid is lost by treatment with pyridine, which is reminiscent of something which we have seen long back when we discussed elimination reaction. If we treat cinnamic acid with bromine, we get the corresponding dibromo derivative via stereospecific anti-addition. And when that is treated with sodium bicarbonate, the bicarbonate ion takes away this hydrogen and a decarboxylative dehydrobromination takes place, where one HBr molecule and overall a carbon dioxide molecule is eliminated, so that we get a vinyl bromine, a derivative of the substituted vinyl bromine. The oxidation of furan in presence of bromine in methanol medium, that is also via the 1,3-diene behavior of the furan molecules. When you treat furan with bromine, the normal reaction is involvement of this alpha position or this alpha position to give you the corresponding oxocarbenium ion, where at the C2 we have the carbon-bromine bond established. Methanol attacks, you get the acetal. Look carefully. From this position, bromine can leave and the corresponding carbocation can be stabilized by the oxygen, giving rise to another oxocarbenium ion, which is immediately quenched by another molecule of methanol. So you have a bis acetal, like situation, which will undergo acid catalyzed ring opening to give you corresponding aldehyde. This one here is from furan. You get, it is the aldehyde version of maleic acid, so we call it maleialdehyde. I leave it to you to find out how this acetal hydrolysis can take place. You should be able to do it. Make sure that you can. Because of the 1,3-diene character, furans are very well-known substrates, dienes, in the Diels-Alder cycloaddition reaction. In the Diels-Alder cycloaddition reaction, you have a diene and you also have a dienophile. And usually it is seen that the diene is an electron-rich species, whereas the dienophile is an electron deficient species. So now you are combining furan with maleic anhydride. Maleic anhydride, because of the presence of these carbonyl groups, is an electron deficient dienophile, and furan, being the pi XS heterocycle, is perfect candidate for the electron-rich diene component. It has these carbon double bonds locked in the S-cis conformation, as well as it has this oxygen donating electron inside the ring, and therefore it is a pi XS heterocycle. So we have the Diels-Alder cycloaddition, where the reaction takes place in this way. So that's a 4+2 Diels-Alder cycloaddition, where you have this formation of the Diels-Alder adduct. Now this maleic anhydride may get incorporated with the furan ring in two ways. One way is that this will be cis to the the maleic anhydride will be cis to the oxo bridge, and that will be, in that case, these hydrogens are cis to the longer unsaturated bridge of the molecule. That's the exo product. We call this exo. Or the maleic anhydride part will be trans to the oxo bridge and cis to the unsaturated bridge, and the hydrogens will be cis to the oxo bridge, and that is the endo product. We cannot go into the details of these transformations at this point. Suffice to say, it is the endo product which is the kinetically controlled product and forms in the reaction medium faster compared to the exo product. Exo product is thermodynamically more stable. As you can see, there is a possibility of static hindrance here. Therefore, that is avoided in the exo isomer, and it is the major product, the eventual major product. But the initially formed product is the kinetically controlled product, endo product. Obviously, there are reasons why this is kinetically controlled, but we will not go into these details here. You will learn about these things in your pericyclic course. The endo product is converted into the exo product via a sequence of cycloreversion. That means this one will, double bond will shift here, this one will shift here, and that one will go there, so that furan is released in the medium and maleic anhydride is also released in the medium. Again, the reaction will now take place, the 4+2 cycle addition will now take place to give you the corresponding thermodynamically more stable XY isomer. So the endo product is the kinetically controlled product and the exo product is the thermodynamically controlled product. And this is a typical example where we see the concept of KCP and TCP working very nicely. The other dienophile that reacts very well with furan is the arine. Remember the Sine substitution that you have seen for aromatic nucleophilic substitution. When we discussed about the SNAR, we talked about this intermediate where a benzene ring has a triple bond. This triple bond, being very weak, reduced by the lateral overlap of two sp2 hybrid orbitals, where the orbitals are not exactly disposed to form lateral overlap, is an extremely reactive molecule and a very valuable substrate for this type of 4+2 cycle addition. This can be generated either from the anthranilic acid by diazotizing this, so that this becomes N2 plus and this becomes CO2 minus, and corresponding loss of nitrogen and carbon dioxide gives rise to this benzene, or from a 1-fluoro-2-bromobenzene treatment with lithium will give rise to breakage of this carbon-bromine bond, so that you have a lithium included here by a metal halogen exchange. That means you have a negative charge here. Carbon-fluorine bond is strong, so a E1Cp type reaction will take place, bad leaving group, but we have negative charge associated with the neighboring carbon, so it will eventually push out the bad leaving group, so that you get the blue benzene. This benzene molecule will act as a dienophile to give rise to corresponding Diels-Alder adduct. This Diels-Alder adduct, when treated with acid, will undergo ring opening to give you access to 1-naphthol, that is alpha naphthol. You will lose a proton here, so that you can establish this carbon-oxygen bond, the carbon-carbon double bond. This double bond will shift and this carbon-oxygen bond will break, because this oxygen under protonated condition, it is a good leaving. When furan is reacted with acetylene dicarboxylate, dimethyl acetylene dicarboxylate, that means you have a carbon-carbon triple bond. On both ends you have CO2 Me groups. Electron withdrawing groups are present. Unsaturation is there. So that's again a valuable dienophile. Furan reacts with it to give you the corresponding dimer, not the dimer, but the Diels-Alder adduct. When treated with H plus, just like this ring is opened up, this also opened up to give you access to a highly functionalized phenol derivative. More importantly, you can chemoselectively reduce the electron-rich double bond, the black double bond of this attack by catalytic hydrogenation, where the electron-deficient blue double bond that is conjugated with the electron-withdrawing groups, it remains intact. And now if you heat this partially hydrogenated product, it will undergo a reverse Diels-Alder reaction and release ethylene in the reaction medium. So the reaction will take place like this. You have double bond shifting here, double bond goes here, single bond breaks to establish a furan nucleus, and this ethylene molecule, being a gas, is escaped from the reaction medium, and that is the driving force of the reaction. So this is a valuable technique to convert furan into its corresponding 3,4 carbomethoxy derivative, which is otherwise difficult to synthesize because it is rather difficult to functionalize the two beta positions of furan ring, because the alpha position is so reactive that functionalization invariably leads to reaction at the alpha. So they can ask for this type of conversion, and you have to think very carefully in terms of Diels-Alder reaction followed by chemoselective reduction followed by reverse Diels-Alder reaction. This is a unique method for the furan 3,4 dicarboxylic acids, because this will be now can be hydrolyzed into the corresponding diacid. So they can even ask you to synthesize the dicarboxylic acid variant from furan. Because of the relatively greater aromaticity, pyrrole rings are generally not susceptible to Diels-Alder reaction. Instead, when treated with dienophiles like DMAD, they behave like enamines and they undergo Michael addition, just as we have seen here. So this is a Michael acceptor, and this is behaving as an enamine, acting as a Michael donor, just like enols or enolates behave, and it is giving rise to the Michael addition product, where we have the central carbon sp hybridized, and just like an alene derivative, which undergoes proton exchange and aromatization to give you the corresponding C2 substituted product. So that's basically a aromatic electrophilic substitution, which is definitely not a cycle addition. But if you are to carry out the cycle addition reaction with pyrrole, you can do that, provided you resist the electron flow of the nitrogen from this heteroatom to the ring. The aromaticity will then be further compromised, and this carbon-carbon double bond will feel isolated from the nitrogen, which is busy in donating its electron pair to somebody else. And then you can think of a Diels-Alder reaction. How can you functionalize this nitrogen? You can form a sodio-pyrrole derivative and treat it with a corresponding acid chloride to give you an N-acylated pyrrole derivative, where the nitrogen lone pair is now cross-conjugated. The aromaticity of this system is compromised because of the presence of this strongly electron withdrawing CO2 group. This time, if you do the Diels-Alder reaction, it will undergo the Diels-Alder reaction to give you the corresponding Diels-Alder adapt, which, if you heat, will undergo reverse Diels-Alder reaction to eliminate shifting the double bond here, shifting the single carbon-carbon single bond to the carbon-carbon triple bond, because you already had a double bond here, and breaking down the Diels-Alder adapt, you will get acetylene, which is a gas, leaves, and you have a 3,4 carbomethoxy dicarbomethoxy derivative of this thing. And this being carbamate, because if you look at this linkage, this is like half amide, half ester. This is a carbamate linkage. It will very readily undergo base hydrolysis to release the corresponding pyrrole derivative when you subject it to proper hydrolytic condition. When pyrrole reacts with benzene, the only product that we isolate is 2-phenyl pyrrole. How does that happen? This is a potential electrophile, this is a strong nucleophile, undergoes alpha functionalization, proton transfer will give rise to this one. However, if Benzynes are reacted with N-alkyl or N-alkoxycarbonyl pyrrole, just like this one, or N-alkyl pyrrole like N-methyl pyrrole, and this undergoes Diels-Alder reaction to give you the corresponding Diels-Alder attack. Just like we have accessed the corresponding 3,4 dicarbomethoxy furan, they have asked you to prepare this one, the corresponding pyrrole derivative. Obviously, the Diels-Alder strategy will work, but Diels-Alder will fail to react on pyrrole. So we have to functionalize this thing. We are functionalizing with tertiary butyl oxycarbonate group, that is a TBOC group with a chlorine associated. So this is TBOX here, tertiary butyl oxycarbonate. So we have this TBOC installed after deprotonation of this pyrrole. We have reacted with the corresponding acid chloride, so the TBOC group is included. Now we react it with the DMAD. Because the electron withdrawing group is present here, Diels-Alder reaction will take place. After Diels-Alder has happened, you can heat this reaction mixture so that you get the reverse Diels-Alder reaction where acetylene is eliminated from this side, and you are left with a carbamate derivative, the so-called urethane, where if you can somehow manage to knock out this group, your transformation is complete. That is done with tosic acid in benzene, and that's a AAL1 cleavage. Protonation here, so you get the plus charge here. Relatively stable tertiary carbocation leaves. You are left with a carboxylic acid. That's basically a carbamic acid derivative. Spontaneous decarboxylation will release the target pyrrole nucleus into the reaction medium. The final reaction that we will discuss in this class is the Reimer-Tiemann reaction. Recall that phenol undergoes Reimer-Tiemann reaction with chloroform and alkali to produce salicyl antimonide. Just like that, when pyrrole is treated with Reimer-Tiemann reaction condition, it gives rise to three different products. One is 2,4-methyl pyrrole, the other is 3,4-methyl pyrrole, and the other one is a little bit surprising, a ring expansion product, 3-chloropyrrole. These two products we can explain by simply assuming that the dichlorocarbene that is produced in the reaction medium can undergo a reaction at the alpha position. Eventual hydrolysis will lead to formation of the 2,4-methyl, or it can attack at the beta position occasionally, so that the 3,4-methyl will result. But how is this forming? So let's just check. So that dichlorocarbene is formed inside the reaction medium. Alpha attack can give rise to this intermediate, which will eventually lead to the corresponding CHO derivative. The hydrolysis mechanism is outlined here, just as you have seen for the corresponding phenol derivative. The hydrolysis is assisted by this nitrogen and finally reveals the formyl group. However, there is a possibility that this dichlorocarbene, instead of acting as a electrophile and getting itself attached onto the C2, that is the alpha position, it may undergo addition across the carbon-carbon double bond between C2 and C3, because carbenes are known to do that. And for furans, this is possible because the resonance energy is low to begin with. For benzene or for phenol, this is unthinkable, because that would mean completely sacrificing the resonance stabilization of the benzene ring. But the resonance energy of pyrrole is lower, therefore this reaction is manageable. When that happens, this three-membered ring will eventually undergo collapsing. This will collapse. There are three ways you can collapse it. One way is this one, where you eventually end up with the same intermediate that you have had here, that will undoubtedly lead to the 2,4-methyl pyrrole. If you collapse it, choose to collapse it in this way, all the time this nitrogen is assisting the collapse. So if you are breaking off this bond, you are getting 2,4-methyl pyrrole. If you are breaking off this bond, then you are getting 3,4-methyl pyrrole. But suppose you have decided to I have made a mistake here. This arrow should not be here. This arrow should be like that. I will correct it once I post the study material, but it is this arrow which is breaking. which is this one which is breaking. But if you choose to break this ring bond, which was actually the ring bond, carbon-carbon C2C3 bond, then you will get the ring expansion product, which also has a name associated with it. This is the Ciamician-Dennstedt rearrangement. Therefore, it follows that if we do the reaction not with CHCl3 but with CH2I2, then our after alpha elimination, our carbene is like that, which adds itself onto the pyrrole nucleus like that, and when it collapses in this particular fashion by breaking of the C2C3 sigma bond, with elimination of HI we get pyridine. So they have asked you this question on some occasions, that how can you convert a pyrrole nucleus into a pyridine nucleus. So that's basically the answer. Similarly, if you take the 2,5-dimethyl variation and do the reaction with the sodium salt of trichloroacetic acid, which is again a source of the dichlorocarbene, you will be ending up with this one. For this reaction, we will come back to this when we discuss the indole. That's the indole nucleus. The Riemann-Tiemann reaction gives rise to the corresponding C2-formyl 2,3. That's the C3-formyl derivative and the ring expansion product. But the 2-formyl product does not form, because if you need to form the 2-formyl, then you need to disrupt the aromaticity of the benzene ring, which is not favorable, either via direct electrophilic attack or via the corresponding 3-membered ring. In that case also, if you want to rupture this bond, you have to push the electrons in this way so that the aromaticity in the benzene ring is disturbed, so that does not form. With this derivative, this is not the only product that you get. For chloroform, if you do the reaction with sodium salt of the trichloroacetic acid, then you get the ring expansion product as the major product. But with chloroform, there is a significant side product, and that is the one which we have also seen for paracresol. For systems like paracresol, we have the abnormal Riemann-Tiemann product where aromatization is not possible. I urge you to look that up and rationalize the formation of this compound via a plausible mechanism. Obviously, the beta position is free, and therefore you can have functionalization here. So 3 types of products are formed when the reaction is done with chloroform in alkali. Finally, there are a little bit of tidbits of information. This is one other important question, that is 2-formyl pyrrole that does not undergo Cannizzaro reaction, but the corresponding furan derivatives do. That's because 2-formyl pyrrole is a vinyl Logos amide, whereas this one here is 5-fural is a vinyl Logos ester. Esters are more electrophilic than corresponding amides, and as we know that Cannizzaro reaction involves nucleophilic attack at this aldehyde carbon, so electrophilicity is important. Because it is less electrophilic, the reaction will probably not take place. And more importantly, perhaps, under the reaction condition of Cannizzaro, which is almost 50% alkali, this hydrogen atom will be taken away and the corresponding conjugate base will be produced, which will further compromise the electrophilicity of this carbonyl group via resonance stabilization. Therefore, we have for furan, we have the corresponding disproportionation reaction, where in one molecule the CHO is oxidized to the corresponding carboxylate, and in the other it is reduced to the corresponding CH2OH, but no such reaction is observed for the pyrrole. Furan to carbonaldehyde, when reduced with sodium borohydride, as we have seen in case of formation of the levulinic acid derivative, you have the CH2OH derivative. Treatment with PCl5 will result in replacement of this primary alcohol with CH2Cl, and that is a substrate which is susceptible to nucleophilic substitution. But the outcome actually depends upon which medium you are doing the reaction. If you are doing the reaction with a powerful nucleophile like potassium cyanide in polar aprotic medium DMSO, it is the direct substitution at this primary center. But if you are doing this reaction in aqueous alcoholic medium, then the cyanide itself attaches itself at this position and you get a 2-cyano-5-methyl derivative. So we have to explain that. In DMSO, the nucleophilicity of cyanide is very high because it is a polar approaching medium, and therefore it does not wait for anyone to do anything. It just attacks the primary aldehyde in a SN2 fashion, releases the chloride in the reaction medium, just SN2 reaction at the primary center. The leading group is there, so what's the problem? There is no problem. But in polar reaction medium, the reaction takes a different course. It is a SN1 via carbocation. This oxygen helps in departure of this chloride, so a resonance stabilized oxocarbenium ion is formed, and that has two different positions that are electrophilic. This carbon, because it shares the most of the positive charge on the side, it is a corresponding relatively hard center, and that is relatively a soft center. Now cyanide, being the soft nucleophile, will choose to attack here, and the aromaticity will be regained, so that you may get the corresponding major product where cyanide is associated not with the side chain but at the aromatic ring. So it is the mechanism is SN1, the pathway is actually SN1 prime, because it is at the allylic position where the nucleophile has chosen to enter. So these two reactions outcome are very different depending upon the polarity and nature of the medium. So this much for this session. I hope that you have managed to grasp the concepts that we have discussed about the pi-XS heterocycles. Next time we will be talking about their retrosynthetic analysis and synthesis. Till then, I thank you for your patience, and I will be seeing you in the next one.